Welcome, everyone, and thank you for joining today's webinar. My name is Samara Ben Reuven, and I will be your moderator for this webinar called Time-of-Flight Technology, Benefits and Applications. Your presenter today will be Chris Baldwin, who is a Senior Application Engineer and Imaging Technology Research Specialist at FRAMOS. Chris is the resident Sony image expert at FRAMOS, and his daily work involves helping customers make their imaging devices operational. Well into his second decade in the photonics industry, Chris has worked with 3D sensing technology from companies around the world and has been part of the FRAMOS iToF development team since the beginning. He evaluated the very first iToF sensor from Sony and is the team leader for iToF product support at the sensor and integrated levels. Chris has spent over 10 years with FRAMOS and is experienced not only with this technology, but also with the quirks and mishaps of making real products in the real world. Before we begin, I'd like to share a few housekeeping rules. All webinar participants should be in listen-only mode. If you do have questions during this webinar, please type them in the questions section of the GoToWebinar control panel, and we'll ensure that they're answered at the end of the event. In addition, a replay of this webinar will be available to you within the next few days. Now, I'd like to turn it over to our speaker and presenter, Chris Baldwin.
Hi, thanks, Samara. Much appreciated for the introduction. So yes, whilst writing this webinar, I remembered all of my history playing around with the 3D acquisition technology, starting from laser triangulation all the way through stereo imaging up to iToF technology. And I even remembered that it's not just a work-related thing, I also do it in my personal life. So this is my Leap Motion. I don't know how many people are familiar with this, but I pre-ordered that in 2012 to show you how long I've been working in this technology, and also how it's for a long time been established as in 3D technology has for a long time been established as a necessity in both the commercial industrial but also in the retail industries. Okay. So anyway, what we're going to cover today is, what is indirect time of flight? Time of flight is relatively easy to understand as it is, but indirect, what does that actually mean? Once we know what it is, we can talk about implementing it, what things we need to do, and then we can move on into the indirect time of flight applications. The skew that I want to put on this webinar is to educate attendees on how the technology works and therefore being able to apply it to a particular environment, because at the end of the day, iToF is a very broad and capable 3D data acquisition technology. You needing to know if it's applicable for your particular desire at your particular time is based on the environment, it's based on the targets, the technology that you have available to you. So, and that's basically, I should have clicked the button earlier to get through these data. There we go. Okay. So first of all, let's talk about why 3D. What is 3D data useful for? So that Leap Motion is a very good one for having a touch-free interface, for example, gathering 3D data from my fingers, being able to fit models to that, being able to see what I'm doing, virtual keyboards, touchless controls. In the era of COVID and pandemics, it's obviously quite useful to be able to interact things without leaving our genetics on them, for example. So, but also, if you're trying to create autonomy, robots that can move by themselves, make decisions on their own, they need to be able to navigate that 3D environment, and they're a 3D object, and so obviously having 3D data allows you to plan, route, and navigate correctly, as well as identify the targets or the obstacles that are in front of that device. So, as I sort of mentioned earlier, indirect time-of-flight sensors are pretty broad. They are mainly focused on giving you a very high resolution, to a spatial resolution, number of pixels, let's say depth pixels per acquisition, and they do that sort of in a scalable way. So currently we're at 640, 480, but there's nothing to say that the technology can't scale. There's excellent depth resolution, so we can select, but by operating these devices in multiple ways, we can get a very good depth resolution from it. Fundamentally, it's an image sensor and a light source that the image sensor is driving, and that can be very, very small. So we can put that into mobile phone scale devices very easily, as well as the traditional 3D requirement people or application environments such as a dashboard of a car, self-driving robot, etc. Another key benefit is that for each pixel that we're obtaining the depth information for, we can also get an intensity per pixel out of that. In fact, that information is available to us as part of the process, so we can use that however we like. So to get into how iToF works, we can just talk very quickly about ping, as I've called it. So just like a sonar sending out a beam of a pulse of sound, the laser can send out a pulse of light. So we turn the light on and off very quickly. That light will propagate out to a target, bounce off it, come back and hit our photodetector. The time between it leaving, and we know when it's leaving because we tell the laser when to turn on, and the time that we receive the detector back is the time of flight. And that is a direct time of flight method. The problem is that although we know exactly when we're going to send out our pulse, we don't know exactly how far away our target is, and therefore we don't know when we will receive the response signal. So we are constantly looking at a very high frequency and a very high precision, trying to determine exactly when that pulse comes back in a sort of a yes/no kind of a scenario. So what we can do is we can move to looking at the phase. So in this diagram, the laser beam turns on. Instead of drawing all of the light spreading out from the laser, I've just drawn the bit that's of interest, the bit that hits our target and comes back again. So we can see that we turn the laser on, and instead of just turning it on for a pulse, we're going to leave that laser on for a period of time. And what we'll see is it will hit the target, come back, and then there will be sort of a difference here. So this is that the time of flight that we mentioned before. So this rise versus this rise is exactly as we saw before. That's not what I'm trying to sort of describe here. What I'm trying to describe is that if we have a look at the full wave process, let's go back. What we'll end up seeing is we'll see exactly the same pulse coming back that we sent out, but it's now shifted. So the start and the end are the same distance away from each other. Effectively, it's the same shape. And we can use that to our advantage. And the way that we use that to our advantage is by deliberately controlling the laser output and the laser output and the detector by having the detector have two sort of different outputs. And effectively, when we turn the laser on, we're going to say, let's collect charge, or let's collect the signal in tap A, and when the laser's off, we'll collect it in B. So basically, A and B are anti-phase. This is 180 degrees anti-phase. I'm sorry, but the word phase gets used a lot in this presentation. They're anti-phase, and at the time of the laser being, they are in, A is in phase with the laser, B is anti-phase with both the laser and A. So basically, the light pulse goes out and it gets started at this point here. So we select tap A. So tap A actually doesn't collect anything. This blue line here represents tap A. We don't actually collect any kind of information at all until the laser actually hits it. So we can now see that lag that we saw before is represented in the start, just here, the start of the integration for the detected signal into tap A. But because we are also, when we switch the laser off, we are also changing from tap A to tap B. We actually cut the integration of tap A and pass it over to tap B. So you can see how what was this single pulse shape here, which is the detected signal, we've now split it over two sample bins. And that's splitting over the two sample bins, and key, well, very, very key, those two sample bins being in phase with the laser diode output, or at a known phase offset, allows us to reconstruct the actual phase location. But we have to do it with more than one pulse. A single laser pulse, in terms of, we have to talk about, we will in the future talk about what frequency it is, and that frequency will determine how long our laser pulse will be on for. And that's actually dominated by the scale of the system, well, the working distance we're working with. But a single laser pulse, for its duration of time, is very, very short. We're not going to have a great deal of light being able to be collected by our sensor. If we start turning up the power in our laser, we'll start melting people and things and basically destroying our target before we get a reasonable single pulse response of this type. So what we do is we actually just have multiple pulses. So we just basically repeat the operation again. Our tap A and B can cycle between each other, and our laser can pulse on and off between each other, and we effectively collect the charge in tap A and tap B to allow us at the end to have a total measure for tap A and tap B as well. In this scenario, I've also put in the fact that there will be ambient light. So, you know, our laser is going to be strong, and we'll have filters to make sure our laser is key, it is dominant, but there is going to be some continuous light falling on our sensor from from the ambient light levels, and that will offset our tap A and tap B measurements. And this is per pixel, but it's so this is a description of a single pixel. All the pixels are doing the same timing at the same in the same scenario. So they're all looking at the same, well, the same laser output is going, and they're all swapping from A to B simultaneously, no matter where the pixel is. So talking about the actual pixel in that array, how is that actually achieved? We've got tap A and tap B. It seemed trivial as I drew it, so I stuck another leg on, but in reality, there's a little bit more work that has to go into it. Fortunately, though, it's not that difficult. Fortunately, it's not that complicated to describe. The best thing to do is to consider a standard imaging pixel. So we have a micro lens, we have a piece of silicon, we have control wires which will be underneath the system, and then we have these two storage locations, A and B. Now, what we can do is we can make all the, on the left here we have incoming photons. These liberate electrons. These electrons can then be moved, collected, stored, and then read out all at once as at the end. So per frequency, or per tap on and off phase, we can select A or B, and we can push the electrons to A or B. Once they get there, they can't leave. They can't get back into the bulk silicon. They can't migrate and cross-pollinate each other. So the idea is that whenever we have enabled A or enabled B, the collected charge for that period will be in that location. So we talked about frequency, and I was talking about the limits that we have to sort of deal with, and we actually start looking at our first equation. There's not going to be too much maths in here. In fact, I've avoided it by doing it some pictorially in a moment. But this is the key equation to look at. Inside the brackets on the right-hand side, for any specific or any selected frequency, that's just a constant. And phi is our phase angle, which goes from 0 up to 2 pi and then goes back down again. It's fundamental to know that we are dealing with an overlap of two repeating frequencies, which means they can only have a maximum correlation of where they're perfectly aligned with each other, which is basically 2 pi or 0, depending on your perspective. What that means is that any measurement that we can create is limited to that distance. Otherwise, distances beyond that will still represent the same phi angle. Phi is the measured phase angle, and m is our distance in this case. So, like I just mentioned, so phase wrap is our sort of limits our minimum, our highest frequency, our minimum wavelength. If we can have more than one cycle that can fit from leaving our laser to coming back to our detector, if we have more than one cycle, we sort of have ambiguity. If something is very close and you get a phase angle of 0.1, and then you move a whole 2 pi distance away and you get a measurement of 0.1 again to the camera, to the system, looking at that phase angle, you'll only have that single phase angle, so you'll have an ambiguity. So this is called the phase unwrapping sort of problem. At the lowest frequency, it's matched more to the practicalities of the laser light. So we can run these things very, very slow if we want to, but the slower we go, it starts meaning that we're trying to push light up to, let's say, 150 meters away. 150 meters is a long distance for even standard lasers to be working when they are sort of spread out the way that we are doing it. So these are an area scanning system. So all the lasers aren't fine points. The lasers are basically turned on and spread homogeneously across our scene. And the further away that you get away from it, the more that you're going to lose your intensity. So it's actually the inverse square law, but we have to obey it twice. Once on the way out, and then once again, that amount of light that hits that target now has to obey the inverse square law, spreading as it scatters back towards our camera. And then we have the sort of high frequency limit is obviously we need to have something that's practical for our measurement system, but we also need to understand that we're dealing with real silicon that actually behaves in a particular way. Okay. So, like I said, I'm going to avoid maths. So this is actually the 4-phase 2-tap approach to removing ambient light, removing any kind of sensor tap behavior. So like we to here, tap A and B are read out individually. And so there's actually 2 different readout circuitry for tap A and B for a particular pixel. That means they could be slightly different. Instead of quantifying that and understanding that based on its power and the angle produced, etc., we actually can just take exactly the same measurement, but completely out of phase. We basically shift everything by 180 degrees. So you can see how effectively tap A and tap B swap positions from this kind of 0 degrees to this 180 degrees change. And when we use all of these 4 measures to build up our actual measurement. But like I said, we don't need to worry about the maths too much, because this, we can just look at it practically, what comes out of the camera or comes out of the sensor. So at least the sensors we're talking today, it's the IMX 570, which we'll get to in a bit more detail later. It outputs in a MIPI format, and we output 4 different phases. Those 4 phases are these different offsets that we have. So here is the tap A and B. This is what we're talking about in the previous how it works approach. And then we need to have these sort of phase offset versions. You need these phase offset versions because we actually need to determine something like this, where tap A and tap B are shared equally amongst these. This pulse is shared equally amongst tap A and tap B, and as you add them all up, it will still be the same. We can't tell if there is nothing there. We can't tell if the pulse is actually at the beginning or the end. And so if we then invert the measurement, we can actually use that to determine exactly when it'll be. But anyway, so the data comes out of the sensor in MIPI. So we have these kind of little mini frames. So this whole unit is a depth frame, and it contains these sort of micro frames, these phase 3. So this is nomenclature from Sony. And anyway, what we first do is to obey the formula that we had before. We take the value of A and subtract from that the value of B. And this is for each pixel. And we end up with C for each one. So we now have a phase for each. So for each of the phases, we have Q0 to Q3, and these represent the difference between A and B. Well, actually, A minus B. The actual sign is needed as well. What we do then is we take Q1 and subtract from that Q3. So this is where we're doing that tap balancing and also that ambiguity of beginning and end type approach. And we generate a value called Q. We do that again with Q0 and Q2, and we get a value of I. And that's what goes into our inverse tan function to create our sort of measured phase angle. And there it is, a little phase angle. Going back to the original formula, as you can see, we have it here. We have our measured phase, which can go from 0 to 2 pi. And then we multiply that by our constant for that particular frequency we're driving the system at. And we receive our distance, which is fantastic. So this is a very simple approach to doing something that would otherwise take per pixel a high degree of accuracy. We need high measurement or high precision electronics. We also need high precision clocks, timers, and a different type of pixel architecture, which ultimately would mean we couldn't have resolutions of this 300,000 plus pixels. So we now end up with this array of measured distances. So now I've got hopefully into your head the idea of phase angle or phase as a direct representation of the distance that we're going at. I just want to go a little bit more through the main details or the main interesting points or concepts that are useful to keep in your head whilst you're looking to apply this technology to your specific application. So the first is that phase ambiguity. Again, the result we'll ever get out of this process for phi is always going to be between 0 and 2 pi. We can't get it any higher than that. What that means is the phi measurement we could have in terms of the real distance, it could be in reality offset by 2 pi or another 2 pi. So effectively this cycle. Now, when I say 2 pi, that's obviously the maximum measurement distance that we have. So if you set up the system at, for example, 120 megahertz, that has a total distance capability of 2.5 meters, which means that your target can be no greater than 1.25 meters away. Otherwise, something that's really close to the camera, as well as something that's right on the edge, behind this 1.25 limit, will appear to have the same phase angle. They'll have other differences, and we can talk about how we can do that, and they'll have other behaviors at different frequencies. But you have to understand this phase ambiguity is something that we need to deal with, and that can come from the frequency selection, the hardware selection, ISP, filtering, data manipulation, etc. The other one is pollution. In my drawing, we had a wonderful laser that only hit our target and only came back to our detector. I mentioned ambient light, which is just a general offset, a DC offset to our whole system. But we also have the potential for our light to go out to our target, hit it, and come back from the same point, but having taken multiple paths to actually get to that location. Bridges of noses, things like this, curved, shiny surfaces can take more light from the ceiling and bounce that straight back into the camera than the light coming out and bouncing straight, going back in again. So what you end up with is multiple paths for a single particular pixel. So it's a real measurement in space of 3D space of a particular surface, or what this pixel is looking at. But there's multiple phase shifted beams hitting that and coming back to our target, and they're all superimposed together. What this typically means, and by the way, the straight line path is normally the shortest path, as you might expect, because it's light. So what you'll find is all these other paths, one, two of them, or even a continuum of these multiple paths will all add up and influence our our standard minimum phase approach, and they will, like that light blue line there, they'll all get pulled away slightly. They'll get longer. So multipath phase pollution has the behavior of extending your measured distance as a result of this. And we have phase pollution of lens impurity as well. So this is it's quite a terrible drawing, but it's just showing the thin lens formula and just sort of describing how the light is traveling through a lens and going onto our target. Now, in reality, the thin lens doesn't work. What we actually have are multiple thick lenses and multiple surface interactions. It's those surface interactions where refractive index changes and actually moves these rays of light around. So if we assume that this path here is actually the path that we're interested in, so this is real information from a target, but it's very, very bright. What we might find is that off certain parts of our lens, we have internal reflection coming. So if this was a movie, it would look like nice lens flare. Maybe it's something that would be tolerable in a machine vision application, because if you assume everything is relatively bright, this whole you'll generally have a glow landing on your sensor, and we can just offset that by saying, well, black, instead of being 0 in terms of digital number, we can say, well, black is anything less than 10. But the problem is that this phase angle approach, these guys here will actually contribute to the pixel's phase measurement that they're landing on. And if nothing else is landing on that, such as there was just black space, there was nothing there, no car in the distance, no doorway, no human, there will still be a measurement there, as this ghost information will land on it and actually provide a measurable phase angle. Now, this is not, so just to say that this blue line versus the gray and the red line, they are taking different paths, but that path difference length is millimeters, if that. So it's not going to be a phase shift because we have a different angle here. We are basically going to get a general illumination across our entire sensor, which is an average of all the bright things on our sensor. So we have to understand, if we see that, we need to be able to create an offset for it. How light levels affect our target is very key. So any measurement that we have is going to be, we are still measuring photons. Photons obey a Poisson distribution. So every time we try to measure them, we're going to have slight variations. So you're going to have that. However, if our system's darker, because we're going to have a higher error in our phase measurement, we're also going to get a higher error in our distance measurement, and that's for very dark objects. So when we're not getting much signal at all, but we are getting some. We also have a similar problem, but when our target is bright and it's got ambient light on it, we're going to have the issue of dynamic range. So first of all, if it's very, very bright, we're going to have an issue just by talking about that internal lens pollution. But if the unit is light and there's a lot of ambient noise or ambient light on it, we now have we've only got one pixel we can fill up in terms of A and B taps that we can fill up. And so if it's filled up with mostly ambient light, and then we then see how much laser light we put on top, we're going to reduce our dynamic range and our ability. This is why filtering is very good, very key. And then another one. So sorry, I don't have a very nice drawing, so I just did this in Octave. The mathematics that we've used is the correlation of sine waves. So it's assuming that we have a measuring sine wave and an output sine wave. But what we actually have is a measuring square wave, i.e. tap A and B, where we're saying yes or no kind of thing. And then we have the actual laser, which definitely just goes on and off as an output. And what that means is the math we're using works correctly for a phase angle measurement for the sine waves. But when we do these do with the square waves, what we end up with is this triangle. So the mass will describe the mass is expecting sine waves, but we're giving it effectively a triangle wave. And so what we need to do is we need to account for that. That's actually not that difficult. You can just make a function of that particular angle and then apply it. Okay, so we talked about the technology sort of at that fundamental level. So hopefully you have a bit of an idea about the phase angle, and instead of just having it of the illumination, it's more the illumination and its interaction with the scene. It just goes maybe half a step deeper than normal. So using that, can we identify some application environments? Yes, we can. It's actually easier to identify application environments by where this technology is more easily disrupted. So point one, very long distances. This system uses a per pixel. It's a per pixel system. So we have 640 by 480, and we put a lens in front of that. So that looks out at the scene. If we want to illuminate that scene, we obviously, based on that lens, we have to sort of start, as our target moves further away, we're going to have to start adding more and more light to cover the total scene that's out there. So maximum distances for this kind of thing is normally assumed to be around sort of 20 meters for general day-to-day objects where we don't have control of the reflectivity of that particular object. You can do a lot of clever things with this stuff as well. So have a look at retroreflectives, not as just as annoying things like we're as a very big cause of high contrast imaging and that pollution we were talking about earlier. But you can also use it to your aid as well with these longer frequencies. So we have that power limit. We're using infrared illumination. Objects such as I have in my test here are packaging materials that are effectively more transparent in the infrared. They are not completely solid, so there's some skin depth penetration. These type of things you need to consider, how it works. So by the way, I can see all of these pretty well, but to get an accurate measure, so I touch it and I am a millimeter away, is much harder because that structure doesn't, optically to infrared, it has a much deeper kind of surface, and we get the superposition of all that surfaces and the scattering, and that gives us our result. So if I was going to touch it, it'd be more difficult, whereas to touch something like this cardboard box, I assume you can see my picture, by the way. It is much easier. So that's something to consider, the light interaction. You can also change the wavelength of the light if you wanted to. High dust and underwater silty environments are not particularly good because if something is very close to our lens floating in front of it, and we shine massive amounts of light trying to illuminate something 4 meters away, we're going to get a very strong response from that one, and that light pollution is going to be much higher. In a normal domestic environment and even dusty industrial environments, it's not really that much of a problem. But if you have lots of material in your way, and I think the silty, ROV underwater robots is a very key one, that might be a bit tricky. But everything else is absolutely fine. Anything that is inside is typically a very good environment. Short distances outside is also a very good environment. There's this lower left one here, which is showing an infotainment system. We are outside where it's very, very bright, but we're still within the the cab of the vehicle, and there's actually not that bright at all in there. So we can again be dominant and use the correct wavelengths. Sort of robot applications, vegetation, this is all very compatible with. Another thing is, if we look into the future at the sort of the lights out warehouse operations and automatic robot navigation, the selection for infrared isn't because of the sensor, it's actually because of it's less distracting to humans. So we can think about the various different ways to improve the application when humans are no longer there. Because flashing lights or bright lights at least are distracting to us. Okay, there's the more sort of different use cases here. So this is something you can look back at when you look at the presentation in the future. But the people counting the demographics, 3D data isn't necessarily, it's always a sort of a step to getting to what you want. So you start with, I need to do A, and you need 3D data to find A. So people counting is a fantastic use for iToF applications. It's very easy to count people's heads from a 3D data set than it is heads from a 2D data set taken from that same location. Hair colors, they mix, shadowing, people of different sizes, so you can't say, hey, anything that I find that's that tall in pixels is going to be a human, because it could be a child versus an adult, just with perspective changes. So time of flight really helps you out there. It gives you that sort of datum for knowing not only how far away something is, but therefore how tall that thing is and how wide that thing is, and potentially how deep it is if you can see the side. So it's very key to understand that although I've been talking about 3D data because 3D is necessary, it actually makes 2D detection, applications that are currently done in 2D easier in 3D. Okay, so we talked about the applications. We talked about the necessity of dealing with these weird and wonderful sort of behaviors for how the light's working, the cyclical error, etc. That would happen in an ISP. So I thought I'd just do a quick layout of two different sort of camera structures. So you would have the sensor, which effectively doesn't drive the laser directly. It sends a signal to a laser driver that drives the laser, and that is the output pulse, which is also driving the internal A to B tap switching. Then the sensor can output over MIPI, all that raw data that I showed in that previous slide, and then the software ISP can just deal with it. There's no need to do anything else if you're going to handle it in your software ISP. However, if you wanted to use a lower powered host device, or your host device is doing something else, so I'm not saying that you have a low powered one, but if you didn't want to utilize the host for doing an ISP, you could do a lot of the heavy lifting on your on a discrete chip. So one thing you do need in this environment is memory. So as we saw, we had those 4 phases that we need to do all that sort of parallel manipulation on. For that, you need to have memory of some type to be able to do that. On a standard SoC, that would be the system's RAM. But if you don't have much of that, or you don't want to use it because it's doing something else, then you could actually get a piece of hardware ISP that has that dedicated silicon inside it to pre-work and do that for you. A typical basic ISP, sorry, wait a second, has to sort of only do a few things. So first of all, the raw data that comes out of the system, you can pass to whatever you like for your processing, AI engines, etc. So having a basic ISP doesn't mean you're doing a basic thing. It just means you don't need that kind of pre-processing done for you. But what you can do in this basic ISP is create your phase angle measurement. You can apply you can do some filtering. For example, one of the Q and the I that comes out, we don't have to just use that for the phase. We can actually use it to estimate a magnitude of the signal that we're seeing, and therefore give us a confidence that are we seeing a strong representation of phase, or is this just happens to be what's created by the noise? So we can do some sort of simple filtering from that perspective. Then you have sort of a more advanced ISP. This advanced ISP can do things like manipulate multiple frequencies together. One thing that's quite nice when you change your sort of phase angle, if you get a particular phase angle for one frequency for one distance, if you change the frequency, you'll get a different phase angle. And you can start combining these to determine the correct phase angle for something. This allows you to increase accuracy at distance, as well as filter out other noise sources and things as well. So that can happen in your advanced ISP. We'd also be saying that this type one would definitely have a calibration, the ability to correct all the fine details, as well as correct for the actual lens itself. One thing I didn't mention is that the phase angle is directly representative of the range from your target to a wall, or target, from your system to a target. So therefore, if you look at your array and you look at a flat wall, it would appear curved, and it would curve away from you because the distance between the point, a point and a wall is different based on the angle you approach it. So adjusting for that, which is just standard optical adjustment, the same techniques used in 2D can be applied, but that would happen in your advanced ISP. Now, very advanced ISP requirements, this can do things such as detection and segmentation and apply 2D and 3D sort of filtering approaches, as well as doing all the fundamentals of this phase, the phase measurement and the phase analysis, that kind of thing. You can also consider the advanced versions to be just throwing raw data at an AI and getting it to learn how to do things. A typical approach wouldn't be to say, let's do everything with this AI, and can it say yes or no to my particular task, but you might use it for doing phase unwrapping. So you'd say, hey, I work in a world of continuously varying surfaces and curves. That means I don't have big jumps. That means that the system can actually look down that, and as it sees the phase angle go round through 2 pi to 0 again, it knows that that isn't actually a change, it's a step. It's not a jump, it's a step change, so it can then adjust itself. Okay. I talked about calibration. Just a quick thing. The way that you calibrate these things is by literally showing it something that you know the measurement distance away, the target is flat or orthogonal to the optical plane for your system, and then you just you would test it, and then you sweep through the phases. You notice here that I say sweep through 2 pi. Obviously, that distance is based on the frequency that you're measuring. And by the way, most of the talking I have has been about just single frequency measurement systems, but putting them together is where the magic is. And so you would sweep through that 2 pi, and then you obviously need to make sure that that is representative of your actual working distance, because that could be 75 meters, for example. Okay, so we talked about well, we sort of moved through the technology through an implementation with an ISP. And so what I want to show you now is the FRAMOS FSM module that we have built on the IMX570. So this is a 640 by 480 global shutter device. So what that means is that tap A and B for the whole array is all sort of reserved at the same time whilst we read it out, so we don't have any sort of other effects. The system has the ability to do up to 8 phases, so we can start saying, well, we need those 4, but what could we do with those other 4? We could do maybe a different frequency, we could do maybe a different exposure range, something like that. We've built this into an operable system, so it's not just a sensor that's delivered, and we'll go into some more detail in the back, but most people will recognize this guy here. This is a Xavier AGX, and it's our typical deployment for our development kits, our technology representations. So just to sort of dive into that, what do we actually got? And this is also a good representation of what you would see in a typical camera device, maybe without the processor back end, of course. But we've got the image sensor, the 570 in the middle. We have a calibration data that we have on an EEPROM next to it. So we actually supply these with calibration files. That calibration file is actually applied by the Sony CXD 5639. So this isn't a product release, but this is a new product from Sony. So this isn't a product release notification, but I got express permission, thank you, to sort of talk about the part number and this depth processor. So effectively, our driver, which is operating on the system, will turn it on the host system, will download that calibration data and push that into the sensor adapter board onto that CXD, and there we'll be able to manipulate further from that. We'll be able to manipulate different filters and different sort of constraints to allow us to get X, Y, and Z data back. So that depth data that goes back into our system. If we go forward from that, we actually have a board on the front, which is a laser driver. We actually have 4 laser drivers, all driven from the same signal from the 570. And then we have the general things you need to make this work: power supply, triggering and timing, and obviously data connections. One thing that is very important is the power separation. So the 570 needs power to flip between A and B. That actually takes a reasonable amount of power. Our lasers need a lot of power. And the CXD is another power device. So what we need to do is you need to be very careful when you're designing a system such as this. Just to say, although it plugs into our Jetson's AVA-GX, it is sort of suitable for plugging into anything using our documented and distributed pixel-mate connector. Okay, I'm over time, I apologize. And I know that I've also had to skim some things. So I hope that there's some questions, and I hope that we have enough time for them.